Hey everybody, in this video we're going to be talking about the plasma membrane. What it's made of, how it functions, how it allows us to live, basically. And I'm going to start with just a really rough sketch of it. So this little thing I just drew here is called the phospholipid. Write that out. PHOS pholipid. And it's actually two of these, so two of these facing away from each other. And this is these two layers composed of the phospholipid bilayer. So this area right here in the middle, where the two tails are meeting, this is called, let's see if I have enough room here, hydrophobic, there we go, zone. Hydrophobic zone, basically meaning that this area in here doesn't really interact well with water or basically molecules that are polar, carry a charge. Next, it leaves us with the hydrophilic heads. Hydrophilic heads. And there's an easy way of remembering this. Hydrophobic, so phobic or phobos is Latin for fear. Fear. While philic or philis means love. So this is this is hydrophobic, water fearing, so hydro means water, and then hydrophilic, water loving. Not necessarily water, but it actually more really corresponds to the types of ions that are attracted to it. By that I mean like hydrophilic, it's ionic, so it mixes well with ions, while hydrophobic doesn't really mix well with ions. What I mean by that is, let's take two types of molecules. We have a hydrogen molecule here, H2. And we have a water molecule here. Let's do nice blue. This is a water molecule. So one of these is polar and one of these is not polar. I'm just gonna give you the answer. Polar, water's polar. Hydrogen is non-polar. So this phospholipid bilayer doesn't really interact well with polar molecules. But it interacts really easily with nonpolar molecules. So nonpolar molecules like hydrogen are able to diffuse through this plasma membrane really easily by going down its concentration gradient. So let's just say I have, hit the button. I have 32 hydrogen molecules on this side, and on this side, scroll up. On this side I have, let's say, 10 hydrogen molecules. So because there's more on this side than on, I did not get myself enough room. Because there's more on this side than there is on this side, and because that these can pass freely through this membrane, because something can pass through and something cannot, it's called semi-permeable. Semi-permeable. These 32 will diffuse across the membrane to the other side until there's about equal on each side. It's not exact because when you're dealing with the numbers of these atoms here, so there's like thousands upon millions on this side and thousands upon millions on this side, you're really just going to get really, really close. You're never going to get exact. So back to the polar nonpolar. So these nonpolar can pass through really quick or really easily, while these These nonpolar can pass through really easily through this plasma membrane, while these polar molecules can't. They have a little bit of difficulty. The polar molecules actually require the help of certain proteins embedded within the plasma membrane, which we'll get to later. What I want to talk about right now is the difference between polar and nonpolar. Just really briefly touch on that. So I want to imagine that there's this electron that these two hydrogens are sharing. It's sort of just floating around here, kind of minding its own business. kind of staying a little bit over on this side, and then goes over on this side. And the reason there's kind of like an equal distribution here is because hydrogen, these two hydrogen, have the exact same pull of the electron, which means, say that this hydrogen is pulling it with force A, and this hydrogen is pulling the electron with force B. And because these two hydrogens are the same atom, they're the same element, they have the same properties, and they're both pulling the electron with the same force. So A is equal to B. This force is equal to each other, which means that the electron can basically just sort of neglect it. It doesn't really notice it that much. It just sort of minds its own business. Kind of hangs around here a lot. Maybe goes to here, but really hangs around here a lot. And because there's an equal pull, this has no charge. There's the electron staying basically the same amount of time on both sides, or staying a lot of its time in the middle. So there's really no charge that this molecule, that this hydrogen molecule has. We'll see that difference with it's different with water, where the electron actually, if we were to map out sort of the probability field of where the electron is. I'm not going to get into what I mean by that, but basically we can never really know where an electron is. We can just sort of guess. And so we'll find that the electron is going to stay really close to the oxygen a lot. It isn't going to go around the hydrogen. It still goes around the hydrogen, but it's going to stay really localized around the oxygen atom. And that's going to actually cause the oxygen atom to have sort of a negative charge to it, because it has this electron. The electrons are negative. So when it's on this side, it's actually really making the oxygen negative. These hydrogen, because it doesn't have that electron there, become positive. So this means that this is really what a polar molecule is. It's just this molecule that carries a charge, and this charge is not equally distributed like it is with this, so that the electron is pulled closer to the oxygen, which makes the oxygen negative, which makes these hydrogen positive, which makes this entire molecule polar. So polar molecules, excuse me, polar molecules have trouble getting through this membrane, and they require the use of proteins embedded within this membrane to allow them to get through. They can't get through otherwise. So I'm just going to copy this and paste it. Paste. Whoops. Should copy it like this. There we go. Paste. Paste. And paste. One more for good luck. Paste. Alright, so let's just make this, let's just say that this is our really small SketchUp of a plasma membrane, just a nice cross section. Now let's say I have this polar molecule A. I'm just gonna, well, let's do a different color. Say I have polar molecule A. I have 17 of them. And I have, let's say, four molecule A's on this side. But because they're polar, they can't cross through this membrane. This wants to get down. Let's say the cell definitely even needs more of these polar molecule A's on the inside of the cell. Let's say inside, outside. It wants more, but it can't get more because this membrane's blocking it. So what's the solution? Well, there's these things called transmembrane proteins. And these are actually proteins that are embedded within the plasma membrane. And they expand the entire width of this plasma membrane. And these are called also part of a class of proteins we'll get to later. I'll go in more detail later. It's called integral proteins. I-N-T-E, is that supposed to be N-G-R-A? Integral proteins. Oops. Proteins. Which are also called intrinsic. Intrinsic. Basically, all that means is that they're attached directly to this plasma membrane. They're not dangling off of anything else. They're attached directly to this plasma membrane. Another type of protein that we have is called extrinsic, or it's peripheral. make sure I spell that right. Yeah, P-E-R-P-H-E-R-A-L. P-R-A-L. Peripheral, which basically means that if there was a protein here attached directly to this membrane, this is assuming it's attached directly to this protein, this membrane, a peripheral protein is one that's kind of like dangling off. So this protein peripheral, this is integral. And so basically that's really the two types of categories of proteins we'll find on the plasma membrane. Either they're attached directly or attached through proxy. So let's go back to our example with the polar molecules. So I have 17 of polar molecule A on this side and 4 on this side, and I want to get all these 17 on this side. So what I'm going to need is a membrane, this transmembrane protein that allows these polar molecules to pass through, because it can't pass through this membrane. It's completely impermeable to these kinds of molecules. So these proteins allow the passage of these polar molecules. The next thing you know, you have an equal distribution on both sides. And that's only because that this is going down its concentration gradient. Because there's more here and less here, it's just going to go down its gradient to balance itself out. So this takes no energy to get down this protein. It will, however, take the energy. If we wanted to get all 17 on this side, it will take energy to allow them to get down. And normally that energy is ATP. Normally, not always though. And it uses ATP, and it allows it to go allows it to go against its concentration gradient, and allows it to go where it needs to be, so that you can all 17 of protein A, of molecule A, and all 4 of the molecule A on one side. Another cool little property about the lipid bilayer is that it's really fluid. It doesn't really. It's gonna do that again. It's really fluid. It's not stationary at all. It really moves around a lot. Actually, really rapidly too. It changes place all the time. Moves around. It vibrates too. It goes everywhere. And while it does move around, it does not mean that it's going to be easy to get in. While it is easy for nonpolar molecules to get through, nonpolar, they can just pass right through. Polar molecules, even though this is moving around and it is shifting all the time, they still can't get through. And they still need the help of these proteins, these transmembrane proteins, to allow passage to where they need to go. This means that the enzymes and the proteins that we find embedded in this membrane generally are not attached directly. They're floating too. This is just a really poor sketch. I really am not going for artistic creativity here. These things are also floating around in this membrane. While these shift here, this is going right over there, and they're moving around all the time. And that's just a really cool thing we need to know about plasma membranes. And that really sums up this I guess, review / learn a little bit of new things about the plasma membrane. In the next video, we're going to be talking about cell signaling. Cell signaling and junctions of cells. Junctions. And these two things are really related. You need, when cells are making tissue and they're really strongly attached to each other through these junctions. And they need to be able to communicate to each other. They need to be able to know what's going on around them, know what's going on with their surroundings. And so we're going to be talking a little bit about that in the next video. If you have any questions, please leave comments. If you have any criticisms, please leave comments. I would love to be able to know what I can do to make this easier, to make this better. If this was the first time you've heard of any of these things, because this was supposed to be mostly a review video, please go to Khan Academy. He's got wonderful videos on really basic parts of this, really basic ideas of the plasma membrane. I'm going to be going into a little bit more detail later. Thank you very much for watching.